got in your M&M bags, you opened them up and listed your number of counts of each color that you got in your M&M's package. So, in the past, we have been able to wonder about one particular color in our bag. And we did earlier this year calculate if the proportion of orange M&Ms in the bag that they claim is 20% that comes off the assembly line, if that could be disputed. So we did a one proportion test, and we tested that claim. And but I want to utilize the entire bag, and I wonder if the entire set of colors, which in this case is 6 colors, follows their claim. They claim these numbers. Called them up. They say that there's 13% brown, 14% yellow, and so on coming off the assembly line. Okay, so basically, we have done one proportion tests. We have done 2 proportion tests. So this test we're learning today is how to handle multiple proportions. Okay? So that's the general idea of what's happening. Now, by the way, we've done one mean, we've done 2 means, and there is a test called ANOVA, which does multiple means, but in this course, we don't get to that. That's like the next thing that we would be doing is the multiple means, and so we don't do that in this course. But you know that movie Moneyball and the sabermetrics, that's built off of the use of ANOVA. So, all right. We want to see if the M&M's company's claim of all these colors is true. So our null hypothesis, okay? So talk to me about that. What kind of things are we talking about? I know it's written there, not to tempt you already, but what's going on? Or what are we wanting to know?
If our color counts actually equal their color count.
Good. We're wanting to know if our color counts actually equal what they say they should. Now, question. What if you get a sample that's a little off? Then do you say, oh, it's not? Okay, what do you have? Kind of what wiggle? What's that called where your sample might be different and it's not too far off, but sampling. Now you're close. Come on.
Sampling variation.
You're getting closer. Variability. Woo! Good. Okay, Laura. Sampling. Variability. Okay, and what again is that saying? That all your samples could what?
Be a little bit off.
Be a little bit off. But if it is not crazy off, then I wouldn't reject the null. Okay, so our alternative in this case is going to be what?
Not equal.
They are not equal. Very good. Okay, so that is how we word in this here. All colors in the M&M's bag are distributed as stated, or all the colors in the M&M's bag are not distributed as stated. This right here kind of gets away from me having to write all these specific things out. Okay, that saves me that. All right, so we know that we are dealing with all 6 colors. This test that does multiple proportions is called the chi-squared. That's chi-squared, not chi, like the styling product, okay? It's chi-squared like the Greek letter, capital X, chi. No, it's not chi, it's chi-squared. You know, you got Sigma Chi, and like fraternities or all those kinds of things are chi. All right. Chi-squared, goodness of fit. What you need to know about the chi-squared goodness of fit, because there are 2 things on your calculator. There's a chi-squared goodness of fit, and there's a regular just chi-squared test. So we are talking about this one today, and the thing that signifies that we're using the goodness of fit is we are only talking about one variable. Multiple categories, but only one variable. What is that one variable that we're wondering about? Multiple categories of it, but just one variable. What? Yay, color. That's right. Color is our one thing that we are testing on the M&Ms. Okay, so our one variable is color. Okay, as always, we have conditions. Let's look and see how they differ from conditions we've done in the past. So right here, you actually don't have to write this out. So this is kind of one that you just need to mentally check. You need to make sure that the values that you have are in actual counts. I'm not interested in what proportion of things you get. So I don't want to know the proportion of your bag that is green or the proportion of your bag that is red. We're actually going to be tabulating the value, how many actually there are, okay? So that's just kind of like, keep that in your mind that you have to have it in that format. All right, so what's our regular first condition? What? Random sample. Okay. Is it reasonable that each of your M&M bags is random samples?
Yeah.
Yep. Okay, we're good. All right. How about independent members, or the probability doesn't change? Okay. Correct. Each of your bags are not apart, so the samples are independent. But listen to this. Does the probability change when I take a sample of one bag out of the population of all M&Ms ever? Is it changing? Is it significant? Is it big enough to change the 13% brown and the 14% yellow and that kind of thing?
No.
No. There's so many, and you pick such a small sample in relationship to this population size. Okay, good. How about our large enough? That is our one thing that is different. Now it's greater than 5. So let's talk. We have 3 different cases. 1 and 2 proportions are large enough. Has to be what? 10. But what has to be larger than 10? For proportions.
Oh, NP.
Good. Okay, so proportions. 1 and 2 proportions. NP and NQ have to be greater than or equal to 10. Good. How about for means? What's large enough for means? Greater than 30. So for chi-squared, and this is the last one we'll have to remember, for chi-squared, it's that the expected count, not what you observe, but what's expected is greater than 5. Okay, so we're actually going to check that right now. So let's check and see if your conditions are met. I want to do one person's together real quickly. No, I need a person that had the peanut butter M&Ms, because is there a difference? I mean, what's going on with the peanut butter M&Ms versus the regular bags? There's a whole lot less. So this large enough might be an issue. Okay, so Rachel, how many do you have in your bag?
6.
No, I mean just
Oh,
like
total?
Mm-hmm.
Oh, I didn't total them. Sorry. 27.
Yeah. Okay, 27. We got 27 in Savannah's bag. Yay. She has her total. Okay.
Oh.
So let's find out. Let's find out what's supposed to be in her bag if these percentages are true. Okay, so you know the claim is 13% brown, so you might want to write this down. The claim is 13% brown, 14% yellow, 13% red, 24% blue, 20% orange, and 16% green. Okay, which of those would give me the most worrisome amount that I need to check? Yeah, the lowest one. Okay, so let's check one of the 13% ones.
Brown and red.
So 13% of 27 gives me an expected value of 3.51. Jinkies. What? You know, is that from the Scooby-Doo?
No,
Okay. Jinkies. Okay. No? Oh, wow. Okay. Okay, so condition not met. Condition not met. So here's how we're going to remedy that. We need a, well, you tell me. How can I remedy that? Nope. Oh, good thought though, but we only did it on me. What's the problem, Matt? What's the problem?
Well, it's probably okay because it's how theirs is.
Nope. Okay, come on. What's the problem? problem is that this number here is not large enough. Hey, guys, here we go. I know it's Friday afternoon, and we've got M&Ms about to be in our blood. Once you've counted, you can eat them, by the way. But we've got the expected value is 3.51. How can I increase that expected value? How?
Get more samples.
Yes. This is too small. I need a larger N. Okay. So all you people that have peanut butter M&Ms, I'm going to combine two random groups together to make one complete random set that is large, that will be large enough. Okay? So it'll end up in this case, if you have a 27 and 25, you got 52 going on. So then that would be large enough. Okay, so let me go ahead and take that time right now and pair you guys up, and then you're gonna end up combining your data. Okay, so if you were a peanut butter person, then you had to combine two of those samples together to make sure that your sample size was large enough. The regular bags did have large enough size. Okay, so right now, I want you to come up with your expected counts, which we already said is the percent times the total. So I want all these expected values filled in now. Okay, so now when you look though at your expected values, again, remember that your expected values do not have to be realistic. Okay, they can be a part of something. Now your counts are real, but your expected don't have to be technically possible. Okay, now the goal here is to see how different, what's the discrepancy in the number of browns that you have? What's the discrepancy in the number of yellows you have? What's the discrepancy in the number of reds? And so then you get a value for how far off those are, and you total up all those discrepancies. Okay, so there's a formula for this, and it is found on your formula chart, which I have a bad copy of your formula chart here. Maybe it's better in your notes, but this is the front of the formula chart, by the way. This is the back of the formula chart. Okay, remember in here is all the standard deviations. This is the confidence interval on the formula chart. This is the back. Right here on your formula chart is the chi-squared value. So if you see this, there is where the formula is. Okay, and that would be like on the yellow formula chart that you use. Okay, so let's let you look at some of those. We'll pass that around also. So find this chi-squared value. Okay, now that chi-squared value is seeing how far your observed is away from the expected. Square that quantity and then divide by expected. So you're seeing how many expected values it is away. All right, I want you to do that for each component. So for example, let's look at my numerical value here. Okay, so look here, we're going to do this formula. Take your observed value, subtract, see how far it is away from the expected. Quantity square, and then divide it by the expected. Okay? Observed minus expected squared divided by the expected. That gives you a value that represents the discrepancy. Okay? This value is discrepancy. And I want to talk about some of these numbers. Some will be really small, and some could be large. And so don't worry if you get a number greater than what's here. Okay, so I'm going to give you a few minutes to calculate all of those components. Okay, so now that you guys all got your individual components, let's talk about what those mean. Okay, so here's my question. What does a component of 0 mean? You're close to expected, so you're so close at 0, so really you what? There is no difference. You got what was expected. So if I found 9 and 9 were expected, then my component would be 0. So the closer you are to 0, the closer your values, your expected and observed, are together. Okay. Well, what's the flip side of that? Here's my example. I have a 2.083. What does that imply as it gets larger? That you are farther away. And it's always a positive number, so it doesn't mean necessarily you have higher or less or whatever. The bigger your component gets, the farther you are away from expected. Okay, so the next thing I want to talk about is the total of all those values. The total of all those values is your critical value chi-squared. Okay, so we've had critical values before. What's a z-star mean? The z-score represent?
How far it is from the standard deviation.
How many standard deviations it is from the mean. Very good. And that's on the normal curve. How about a t-star or a t-score? What's that? The number of standard deviations away from the expected on the t-curve. Okay. Technically, when that standard deviation is made from the sample, it's called a sample error. So how many sample errors you are away from the curve. Okay, so chi-squared is that same idea. It's how many discrepancy units, and we're not going to talk about those discrepancy units, you are away from expected. Okay, so let's now talk about what the shape of the curve looks like, because it's not normal. It looks very, 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 very different.
It almost looks like a chi-square, kind of.
Okay, so now here you may notice that we have degrees of freedom. Here's degrees of freedom 1, here's degrees of freedom 2, degrees of freedom 3. Okay, so question is, how do you think degrees of freedom are tabulated?
N-1.
Okay, n-1. That's what we've done in the past. Very good. So that would mean like your number that you had in your sample minus 1. Well, in some cases that could be, 50, because 51 minus 1 could be 50. That is not the case for chi-squared degrees of freedom. Okay, so here we go. This is another difference. Okay, chi-squared degrees of freedom are based on the categories. How many categories did we have? We had 6. We had 6 different colors. We had 6 categories. So our degrees of freedom would be 5. Okay, so we're dealing with the degrees of freedom of 5. Okay, very good. So what happens with these curves is that the farther you go along and the higher you get in your degrees of freedom, so the more categories you have, then the flatter this curve falls out. Okay. So, now let's talk about the mechanics of one-sided or two-sided. What do you notice about the domain of this picture? Domain is the x values. What do you notice about the domain of these curves?
Can't be less than 0.
Very good. You
What is that for?
cannot have a negative chi-squared value. So the domain is always greater than 0. Okay, good. So therefore, can you have a two-sided test?
No.
You cannot, because we only have one side. So the most you can have on these is one-sided. All right, very good. Okay, so let's now decide, based on that critical value chi-squared, let's decide if we have enough evidence to reject or fail to reject. Okay, so we're wondering if our value is really weird. Is your chi-squared value crazy high? Okay, well, we don't know. It's not like 2 standard deviations out or 3 standard deviations out, because these numbers are quite a bit bigger, okay? These numbers, so let's go ahead and look at your chart. Look at your cream chart that you have. You have the T side of the chart, okay? And then you have the chi-squared side of the chart, okay? So get that out. All right, so identify, I wish I had a better picture of this. I might have one up. So identify where 5 degrees of freedom are. Okay, so look over here on the left. This is your 5 degrees of freedom. Okay? All right, so what's our typical p-value to where we would say that we have statistically significant results?
0.05.
Okay, good. 0.05. So locate that up here. 0.05 at the top. Okay? Okay. So 0.05 is located right here. So what that means, and these are all, this column represents all of your chi-squared values. So, what is this number at 5 degrees of freedom at 0.05? Of course, you can't see it on mine, but if you look on your chart, that number is 11.07. Okay, so let's interpret that. Okay, 5 degrees of freedom at 5% significance level is 11.07. So if you're chi-squared, so where on this T-chart or this chi-squared chart, where is this section that you end up rejecting the null? That means your p-value is going to be what?
Greater than.
No, less than 0.05.
But greater than.
Okay, less than 0.05, correct. Greater than the critical value.
Yes.
Yeah. Okay, so less than 5%. Where is the area of the chart that you reject? To the right. Very good. All of these probabilities go down. So these probabilities get smaller. So on this side of the chart is where you reject the null at the 5% significance level. What's the quality of all of these chi-squareds in here? They're getting what? Good, they're getting larger. So the larger your chi-squared, the more likely you are to reject the nulls. Okay? Well, let's do the flip side. See on the flip side. So over here on this side, these probabilities are not too strange. What would be our decision over here on this side? Fail to reject. Okay. Because why might I have a value in here? These are smaller chi-squared values. Why do I have any at all? I mean, these mean you're closer to expected, but not far enough away to be significant. Why? How can that happen? Because of sampling variability. Good. Sampling variability. So you could have, some stuff over here in this area, but that's not significant enough. It's not far enough away from expected. All right. So let's interpret your results. Let's find your p-value. Okay? Oh, well, actually, we could just go ahead and look. How many of you guys that had the regular M&Ms had a p-value larger than 11.07? Okay. So nobody did. So did we find any evidence on any of these samples to...
11.07?
Yes.
I had 11.66.
Okay, you had 11.66, so you were just close in, okay? All right, so what do then we say to the M&M's company? Do we have evidence to reject their claim? No, we do not. It could be as stated. Could be those percentages. Okay, well, let's go with peanut butter people. Okay, peanut butter packs, all you peanut butter pairs of people, then any of you guys find a chi-squared number that's larger than 11.07. What you guys got? 13.8. Okay, 13.89. Anybody else? Any other peanut butter groups get a large enough chi-squared that you end up rejecting? Okay, No. So we had one peanut butter group that ended up rejecting. Okay, so thoughts on that? Does that mean when I call up the peanut butter company later, the Mars Candy Company later, and I say, can you tell me the percentages for your peanut butter M&Ms? They could be what? They could be the what? As stated. Good. They could be as stated. They could be the same as what the regular M&Ms are. We don't have evidence to suggest otherwise. Now, this one particular group did. Okay, so let's think about that. Out of the whole day, I had one particular group that found, that's not true, it wasn't really out of the whole day, but let's just say it was out of the whole day. I only had one group that found a quote-unquote rare sample that caused us to reject the null when indeed it really is not false.
Type 2.
Woo! Okay, well, good. Okay, let's see which one it is. Type 1 means the null is true, but we found a rare sample, and we ended up rejecting it. Okay, so it is type 1. Type 1, the null is true, and we found a rare sample and rejected. Good. So see, they would be going through life saying, hey, the peanut butter candies aren't the same distribution as the regular ones, and that would be an error that they would be making, but they don't know they're making it. Okay? All right, so that's basically it. However, I would like to show you the calculator trick to do these things. So, everybody go into your calculator and go into your list. And I need you to put your data, your observed goes into list 1. Let me get back over here. Your observed goes into list 1, so put your observed into list 1 and your expected into list 2, and those are the only two things you input. So do that now. I want everybody inputting those pieces of data into your calculator now. Alright, so let's actually do the computing. You have your lists in. You do not have to put the components in, so watch this. Stat, over to tests. It's easier to go up to the bottom of the list. So go up. Oh, by the way, look at that ANOVA. ANOVA is the one we won't get to. That's the bunch of means. That would be the next thing that would happen. Right here, chi-squared goodness of fit. And if you have a TI-83, that's the second command that you don't have on your calculator that everybody else does. Because chi-squared goodness of fit is different from the chi-squared test. Okay, so you have to do the goodness of fit. So if you hit that number, then you got L1 is the observed, L2 is the expected, and degrees of freedom. And then you calculate, and those numbers should be the same thing that you calculated by hand. Okay, homework, 4 problems, and you know what? You know what number you should be to on your little packet? 50 by Monday. If you've been doing 10 a day, I'm checking that you've gotten to 50 by Monday. So you're behind. Okay. Yes.